Let's take a look together at the notes for section 5.7. This is over probably the most important topic of the semester with substitution integration. So what I want to make sure I show you in a section like this is up till this point with our basic techniques of integration, we haven't been able to integrate something like the integral of 2x times the square root of 1 plus x squared with respect to x. Because it's not integrable with our basic rules. We have no way to distribute that x into that square root in a manner to where we could use the product rule after that, because we'd still have a group to a power even if we were able to say that that was the square root of 4x squared and distribute it through. So there has to be some other techniques to help us out in these problems, and the technique in this section is called substitution. Now, typically when we use substitution, we're going to use the variable u to represent part of the integral. And you'll notice here in parentheses, I said it's usually the innermost part of the function. So in this case, if you looked at this integral here, you can see, well, 2x, it's not inside any function. However, the group 1 plus x squared is inside of a square root. So it is a function inside of a function. It's the innermost part of this function. So most likely, that's going to be our most useful choice for the u substitution. I would let u equal 1 plus x squared. In fact, that is what turns out to be helpful in this problem. Now, the goal of substitution is to take something that we cannot integrate and make something that we can integrate. And it's really nothing more than the reverse of the chain rule from Calc 1. In Calc 1, we said that the derivative of g of f of x is g of f of x times, is g prime of f of x times f prime of x. Well, now, what if I have a function g and f of x inside of it, and then I have the derivative of f of x on the outside of it? Well, then I'll be able to integrate that and say, I'm going to put that function on the inside, let's call it u. And then I know that everything on the outside, it's just going to be du. Now, I've tried to show that here. If I say, well, if I let u equal f of x, then the derivative of u with respect to x would be the same thing as f prime of x. So then du is going to be f prime of x times dx. That f prime of x dx just gets replaced with du in our problem. And then we integrate the function g of u with respect to u. And it's not going to be too bad at all. Now, first problem here, it's the one I referenced up here. If I have the integral of 2x on the square root of 1 plus x squared, I want to integrate it with respect to x. So again, I'm thinking of that square root of 1 plus x squared. That's my g of f of x. F of x is the 1 plus x squared. What's happening to it? Well, it's inside the function g, which is the square root of x. Now, my derivative of the inside would be the 2x dx. So this problem is going to work out gorgeously. Everything I need is already there. So for my substitution, I'm going to say, let's let u equal 1 plus x squared. If u is equal to 1 plus x squared, then I know that the derivative of u with respect to x would be 2x. Now, from now on, let's just go ahead and make the shortcut in saying from u to du. It's because I want to replace dx with du in my problem. If the derivative of u with respect to x is 2x, you can think of that du dx as a fraction. It literally means the infinitesimally small change in u over the infinitesimally small change in x. So that dx can be multiplied to the right-hand side, and I just get du is equal to 2x dx. So now I go back into my problem and say, well, then this original integral, 2x on the square root of 1 plus x squared dx, the 2x dx becomes du. My square root of 1 plus x squared becomes the square root of u. So then I get the integral of the square root of u du. That's going to be u to the 1/2 power. So its integral is u to the 3/2 power times 2/3, of course, plus the constant of integration. Now, after you do that, once you get your answer in terms of u by integrating with our basic rules, then we know u is equal to the group 1 plus x squared. So my final answer here would be 2 times the square root of 1 plus x squared raised to the third power all over 3 plus your constant of integration. Of course, you could also have brought just 2/3 times this group to the third power too. I chose to put it in a fraction like that. Now, you can always, if you have any doubt, you could take the derivative of your answer and it must lead you back to your original expression. Notice if I took the derivative here, the 3/2 would come down in front, cancel out that 2/3. Then you'd have 1 plus x squared to the 1/2 power, which is the same thing as the square root, times the derivative of the inside. Well, that's the 2x. And of course, derivative of any constant, 0. We get what's left on the inside with our derivative answer, as we always should. Now, let's look at another one here. If I have the integral of the square root of 2x plus 1, and I'm asking you to integrate that, again, with respect to x. So I can say, well, all right, the function inside of the function, clearly, u needs to be 2x plus 1. The derivative of that is going to be 2 with respect to x. Then I can say, well, okay, I don't have a 2 dx in there, but I can always put it. So in the inside, I need to see a factor of 2 dx. So I multiply by 2 on the inside. I can do that as long as I divide by 2 on the outside. So I'll get 1/2 the integral, the square root of 2x plus 1 times 2 dx. This 2 dx becomes du in the next step. The square root of 2x plus 1 becomes the square root of u. So very similar to the last problem, I'm integrating u to the 1/2 power. So I'll get u to the 3/2 times 2/3. This time it has a multiplication factor of 1/2 in front of it. So that's going to give me 1/3 u to the 3/2 plus your constant of integration. When we go back in and substitute, we know that u is the group 2x plus 1. This is going to be the square root of 2x plus 1 raised to the third power. You can raise to the third power inside the root or outside the root like I did in the last problem. It's totally inconsequential which notation you use. They're both correct. For another one here, I know what you were thinking. You're thinking, well, hey, these are going to be ideal problems for trigonometry. Absolutely. In this problem, the function inside of the function, I have x to the 4th plus 2 inside of the cosine function. So I'm going to automatically think I need to let u equal what's inside of that cosine function, the x to the 4th plus 2. If I do that, I know that the derivative of u would be 4x to the 3rd with respect to x. So I go back to my problem and I can see, well, I don't have a 4x to the 3rd dx. And in order to do this substitution, I would have to have a 4x cubed dx. Well, that's easy. I can just say, well, then that means I need to multiply the inside by 4 and divide the outside by 4. No problem. You can always multiply by any constant factor on the inside and then divide by that constant factor on the outside. You cannot manipulate variables. Like, what if I needed a 4x to the 5th in there and I just had a x to the 3rd? I'd have been out of luck. That would not have been a possible substitution. But you can always multiply by a constant on the inside as long as you remember to divide by it on the outside. Now, from this step to this step, I see that the 4x cubed dx, that's going to become the du. The cosine of the angle becomes the cosine of u. Integral of the cosine, I know since derivative of sine is cosine, the integral of cosine takes me backwards to sine. I still have my 1/4 multiplying it, plus the constant of integration. And then when we say, well, okay, now what about the angle u? Well, I can see that the angle u is just representing x to the 4th plus 2. You'll always want to put it back in terms of the original variable of the problem. So I get 1/4 sine of x to the 4th plus 2 plus your constant of integration there. Now, for the next page here in my notes, and each of these problems should get slightly more difficult as we go. I tried to start off easy and I worked towards beautiful in these examples. And number 4, we have the integral of x over the square root of 1 minus 4x squared. And I'm asking you to integrate that with respect to x. Again, The rule of thumb is to always let u equal what's the innermost part of the function. Well, I have 1 minus 4x squared inside the square root. That should automatically be your initial choice for u. So I try that. And I can say, well, the derivative of that's going to give me negative 8x to the first times dx. I have an x dx, but I don't have a negative 8x dx. Okay, I'll multiply by negative 8 on the inside. I can negate that by dividing by negative 8 on the outside. So I have 1 over negative 8 on the integral of negative 8x dx. I know that all of that negative 8x dx is going to become du whenever I use substitution. The square root in the denominator is going to become the square root of u. So this simplifies gorgeously to negative 1/8 times the integral of 1 over the root of u du. Now, on that inside, I didn't show it, but you should be thinking that's nothing more than u to the negative 1/2 power. So when you integrate u to the negative 1/2, you add 1 to the exponent, so it's going to become u to the positive 1/2 power, divided by 1/2, which means multiply it by 2. I'm going to get 2u to the 1/2 plus c when I integrate. That's multiplied by the factor of negative 1 over 8 that was out in front. I'll get 2 times negative 1 over 8 is negative 1/4. And then this is going to be the square root of u plus your constant of integration. And then when I substitute back in for u, I say, well, u is this group right here. The way I chose to write my answer, I think it looks better to have the 4 in the denominator. I'm not really a fan of putting fractions in front of roots, but you can. But I would rather say this is the negative root of 1 minus 4x squared, all divided by 4, and then plus your constant of integration. Okay, now, all of the ones we've done thus far have at least been fairly straightforward. What I mean by that, the first one, the exact substitution I needed was automatically in there. Problems 2, 3, and 4, what I needed wasn't in there, but it was just a constant multiple away. So I had to multiply by 2 and 2, I had to multiply by 4 and number 3, and I had to multiply by number 8 and number 4. Now, number 5, notice it's a bit more tricky. First of all, you cannot algebraically simplify easily because I don't want to have to expand that group out to the 7th power. It would be an 8-term polynomial function. Please don't think that that's just x to the 7th plus 5 to the 7th. That's never, ever true. It'd be an 8-term polynomial that then I would have to distribute an x through. So instead of having to do it the messy way, I'll do it the smart way. Smart way is substitution. You let what's the innermost part of the function be u. So u is going to equal x plus 5. But then if I take the derivative of that, derivative of x with respect to, that's just 1 with respect to x. So yeah, I can see that dx is going to become du, and that the group x plus 5 to the 7th, that's going to become u to the 7th. However, I've got that x in there that did not cancel out with a substitution. No big deal. This gives you an equation to represent x in terms of u. So as soon as you say u is equal to x plus 5, automatically you can imply, well, then x is equal to u minus 5 with a simple algebraic step. So now I go into my problem. I replace the x with u minus 5, the x plus 5 to the 7th with u to the 7th, and dx with du. And now you might think that you're no better off than where you started, but you're so much better off, because where originally you couldn't simplify that algebraically very easy, now you can. You can distribute the u to the 7th through this binomial and get u to the 8th minus 5u to the 7th. And then we just use the power rule on each of those terms. The first term becomes u to the 9th over 9. Second term minus 5u to the 8th over 8. And then, of course, plus our constant of integration. When we get our final answer back in terms of x, notice the only thing I've done from here to here is everywhere I saw a u, I replace it with an x plus 5 for my final answer. Now, what about exponential functions? We remember that the derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base. So since integration should be the reverse of that, the integral of any exponential function should be that exponential function divided by the derivative of its exponent and divided by the natural log of its base. So I could just quickly look at this problem and say, well, hey, how do I integrate 5 to the pi x? I know it's an exponential function. Integral of any exponential function is that exponential function divided by the derivative of its exponent and the natural log of its base, plus the constant of integration. You could be done. Now, this problem is wanting us to emphasize substitution, or this section is wanting us to emphasize substitution. So you can show the substitution in the problem and say, well, u is equal to the function inside of the function, which is just the function in your exponent, which is pi x. We know the derivative of pi x with respect to x is just pi. So du is pi dx. And you notice this substitution is impossible right now because I don't have a pi dx. Well, then I can multiply by pi on the inside if I divide by pi on the outside. So this is going to give me 1 over pi times 5 to the pi x times pi dx. The pi dx becomes du. The 5 to the pi x becomes 5 to the u. But even with that substitution in there, you still have to understand how to integrate an exponential function. So I'd say, well, then the integral of 5 to the u is going to be 5 to the u divided by the derivative of u with respect to u, which was just 1, and then divided by the natural log of the base, which is natural log of 5, plus your constant of integration. And then you can say, well, this 1 over pi that I had to divide on the outside in order to enable this substitution multiplies through. That's going to give me 5 to the pi x divided by pi natural log of 5 plus c. Now, the next problem I want you to see is a gorgeous trig function like this tangent function. You might recall from Calc 1 that we never had any derivatives of our basic trig functions that resulted in a tangent. We know that the derivative of tangent is secant squared, but we don't know what we can take the derivative of to get a tangent. So since I can't think in terms of Calc 1 derivatives to answer this question, what I would like to go ahead and do is, well, let's break tangent up into sine over cosine. Now, automatically, whenever you have a fraction, you have an implied function inside of a function. It's not obvious, but that denominator, that's saying, well, that cosine of x is really raised to the -1 power since it's in the denominator. So if I had to think of anything that's inside of a function, it's not the numerator, it's the denominator. So anytime you have a numerator and denominator, I will say 99% of the time, the u substitution is going to be to let u equal that denominator. I do in this case. U is equal to the cosine of x. Well, the derivative of cosine x we know is the negative sine of x with respect to x. I don't have a negative sine x in the problem. No big deal. I multiply the inside by a negative. I make up for that by multiplying the outside by a negative. You can always multiply by any constant on the inside and outside to make up for it. Okay, so now this negative sine x dx I know is going to become du. I'll have 1 over cosine, that's going to become 1 over u. So I have the integral of 1 over u with respect to u. We know that the integral of 1 over u is going to be the natural log of the absolute value of u. And then we have plus our constant of integration. We'll still have the negative out in front of it. That didn't go away. So my answer is going to be the negative of the natural log of the absolute value of the cosine function plus your constant of integration. Now, if you looked this problem up in the table of integrals in your book, it's not going to give you that answer. It gives you this answer. Keep in mind they're the exact same answer. I actually prefer this one myself, but where this answer is coming from is we know that one of the properties of logarithms is that any coefficient could go up as an exponent. So I can say this -1 coefficient can be written as the natural log of cosine x raised to the -1 power. Well, cosine x to the -1 power is the reciprocal of cosine x, which that's going to cause that to be the secant of x. So either one of those saying the same thing. Now, you're thinking, hey, this is pretty fun stuff. It is. Substitution is glorious. Now, what have we not done? Well, I haven't given you any definite integrals. Definite integrals gives you something you definitely need to think about here. So let's say I wanted you to integrate from 13 over 2 up to 16 of the cube root of 2x minus 5 with respect to x. So first thing, before I even worry about the limits of integration, I just think, can I do the substitution? Sure. The u would be what's inside the group to the power of the 2x minus 5. My du, derivative of 2x minus 5, is going to be 2 with respect to x. I don't see a 2 dx in the problem, but that's okay. I know I can put a 2 dx on the inside if I remember to divide by 2 on the outside, and then that's going to enable that dx, that 2 dx, to become du in my next step. So I've taken care of that by multiplying by 1/2 on the outside and calling dx du. Then my cube root of 2x minus 5 can be rewritten as the cube root of u. But while I do that, these original limits were in terms of x. Whatever the dx is telling you what these are in terms of. So this is with respect to x as x goes from 13 over 2 to 16. If I'm going to change this substitution to terms of u, then this has to be in terms of u as well. Go back to your u formula. We have let u equal 2x minus 5. Evaluate that at 13 over 2. I would get 2 times 13 over 2 minus 5. That's going to give me 13 minus 5 is 8. My newer lower limit of integration is not 13 over 2, but instead 8. My upper limit, you replace a 16 in here, you'd have 2 times 16 is 32, minus 5 is 27. That's what I've done over here. And so I can say, instead of integrating from 13 over 2 to 16, I'm integrating from 8 up to 27. Now, I'll integrate that. This is u to the 1/3 power, which becomes u to the 4/3. Then dividing by 4/3, same thing as multiplying by 3/4. What I would like to do in that step is I'll go ahead and say, well, this 3/4 and this 1/2, that can be multiplied out to 3 over 8. I did. And then I'm going to have u to the 4/3, or in other words, the cube root of u raised to the 4th, evaluated from 8 up to 27, which means we evaluate it at 27 and then subtract the evaluation at 8, multiply both of those answers by 3 over 8. That's what I've done here. If I have 27, I know that the cube root of 27 is 3. 3 to the 4th power, 81. My upper limit, 81. My lower limit, 8. Well, the cube root of 8 is 2. 2 to the 4th is 16. I have 16 as my upper limit minus lower limit. 81 minus 16 is going to give me a 65. 65 times 3 over 8 gives me 195 over 8 for a nice final answer there. Now for the next one here. What if I give you a definite integral again, this time from 1 to 2 of dx over the group 3 minus 5x quantity squared? There should be no question what you should allow u to be, and that's the group in the denominator, the 3 minus 5x. But if you do that, you see that the derivative of u would need to be -5 with respect to x. I don't see that in there. So you'll see from this step to this step, all I've done is I multiplied by -5 on the inside, divided by -5 on the outside. Everything is still in terms of x, so I left my limits of integration in terms of x. But now from this step to this step, I want to get rid of x and put it in terms of u. -5 dx becomes du. The denominator is going to become u squared. My limits of integration, I plug 1 into my formula for u. U of 1 is going to be 3 minus 5 times 1. That's 3 minus 5 is -2. My lower limit of integration is -2. My upper limit of integration is when you plug in a 2. That's going to be 3 minus 5 times 2. Well, that's 3 minus 10 is -7. We're integrating from -2 to -7 of this function. Now, when I'm looking at that on the inside, I would prefer to think of it as u to the negative 2 power. That way, when I add 1 to the exponent, I can say, well, that's going to become u to the negative 1 divided by negative 1. That's the same thing as negative 1 over u to the first power. So this integrates to become negative u to the negative 1 power, negative 1 over u to the first power. I still have my negative 1/5 out in front. I need to evaluate this from negative 2 to negative 7. Now, what I went ahead and did in this case, especially since I had a negative times a negative, I just multiplied that and said, well, this is the same thing as evaluating positive 1 over 5u from negative 2 to negative 7. When you plug in the negative 7, your denominator is going to be negative 35. You'll get negative 1/35 minus the lower limit. But I know that the lower limit's going to be negative. Instead of saying minus a negative, I just went ahead and said plus a positive, and it's going to be 1 over 10, 5 times 2. So I have 1/10 minus 1/35 gives me negative 2 over 70 plus 7 over 70 for 5 over 70, which of course reduces as a fraction to 1/14, which I think as a decimal is like 0.0728571428. Pretty cool. Now, up next here, number 10. Again, I'm giving you one where we have a definite integral here. I'm asking you to integrate from 1 to e of the fraction, the natural log of x divided by 3x, and are integrating this with respect to x. So just like some before, I can say, well, I need to try something for my substitution. Now, unlike the ones before, especially where I had fractions and I said, let u equal what's in the denominator. I don't want to let u equal what's in the denominator here. That wouldn't help at all. But if I let u equal the natural log of x, then I know that the derivative of the natural log of x is 1 over x. And I have a factor of 1 over x in this problem. Keep in mind, this could be rewritten as the natural log of x over 3 times 1 over x dx. So since this first part can be written as the natural log of x over 3, how about I just factor that 3 to the outside as a factor of 1/3? That's the same thing. So that's exactly what I did. I said, it doesn't matter whether the 3's in the denominator on the inside or on the outside. I'm just factoring that out. Now, please don't get that confused with where I had to do something in the last problem like, well, I thought when you multiply by something on the inside, you have to divide by it on the outside. You absolutely do. Sometimes people get this and this confused. I didn't multiply by anything on the inside. I'm just taking an existing 3 that's on the inside that I don't need in there and factoring it out. It's a 3 in the denominator on the inside. It's a 3 on the denominator on the outside. You could have also thought of it as, well, another way to get rid of that 3 is by multiplying by 3 on the inside. If you multiply by 3 on the inside, you have to divide by 3 on the outside, and 3 over 3 on the inside would cancel. However you think about it, you need to understand it comes out as a 1/3. Now, I haven't changed anything else other than factoring out that 3 in the denominator. And now I'm looking at this as natural log of x times 1 over x dx, which will be very nice for my substitution. Since I know my substitution is going to work very well and just be u du, I change my limits of integration. U evaluated at 1 is the natural log of 1, which is 0. U evaluated at the top limit, e, natural log of e, we know that's just 1. So I'm integrating from 0 to 1 of u with respect to u. And when I integrate that, power rule says it's going to be u squared over 2, evaluated from 0 to 1. Sorry, I got a little sloppy there. When I plug in the 1, I'll get 1 over 2. 1 over 3 times 1 over 2 gives me 1/6. Why didn't I worry about the lower limit? Because it's 0. It's just going to give you a 0 anyway. Now, back to an indefinite integral. So let's say I have something like number 11. We saw something similar to number 11 in number 5 where I said, it's a little bit of a tricky one where we had a variable left in there that we had to account for. This is going to be the same idea here, except kind of a more difficult case of that problem. So Whenever we look at this, you say typically you let u equal the innermost part of your function. In this case, that's the x cubed plus 1. That should be your choice for u here. So if u is x cubed plus 1, but then the problem with that is the derivative of u is going to be 3x squared with respect to x. So I see I have an x to the 5th dx, not a 3x squared dx. Well, I need to see a 3x squared dx in there in order for substitution to be used in this problem. So here's what I did. I had to, now again, please remember the difference in what I'm doing here and what I did here with factoring out that 3. I did not have a 3 in this problem, so I am multiplying the inside by 3, which means, well, then you got to make up for that by dividing the outside by 3, or bringing the 1/3 to the outside. 1/3 times 3 would cancel, and all would be good. But on the inside, I needed that 3x squared times the dx because that's going to become du in the next step. Well, I'm going to have an x cubed left over in there that the substitution doesn't get rid of. So I'm using my formula for u. I know u is equal to x cubed plus 1. So I know x cubed is equal to u minus 1. So then I can say, well, from this step to the next, when I'm trying to put it in terms of u, I can say my square root of x cubed plus 1 just becomes the square root of u. My 3x squared dx becomes du. My x cubed becomes the group u minus 1. And of course, in order to make all that happen, I had to multiply by 3, which means I had to divide by 3 on the outside. It's still there. Now, the nice thing about this is I can algebraically simplify and distribute that square root of u, which is u to the 1/2 power, times u minus 1. And on the inside of the integral, I'll get u to the 3/2 minus u to the 1/2. Both of those integrate really nicely by the power rule. We add 1 to the exponent here, you get 5/2. So please keep in mind you would divide by that new exponent, or multiply by its reciprocal. We'll get 2/5 u to the 5/2 minus, this is going to become u to the 3/2 times 2/3, dividing by 3/2, plus our constant of integration. Every bit of this is still multiplied by the 1/3 out in front. So for my final answer here, I would get 2/15, and you could say times the group x cubed plus 1 to the 5/2 power. It looks better since the original problem was in radical form to have your answer in radical form. So I'll say 2 times the square root of x cubed plus 1 raised to the 5th power all over 15. When I distribute the 1/3 into the second term, I'll get minus 2/9. So I'll say minus 2 times the square root of this group x cubed plus 1 raised to the 3rd power all over 9, plus your constant of integration. Okay, pretty good problem there. Next page here. If I look at this one with you, I can say, well, I have the integral of x squared with respect to x. We're dividing that by x plus 5 cubed. So automatically you say, well, we're supposed to let whatever's inside of a group to a power be u most of the time. So the obvious choice for u is to let u equal x plus 5. Well, then du is just 1 dx. That doesn't help get rid of the x squared in the numerator. This one you're going to have to work a little bit harder on. So I know that if u is equal to x plus 5, then I know x is equal to u minus 5. I don't just have an x that I have to get rid of in that numerator, though. I have an x squared. So x squared would equal the group u minus 5 quantity squared, which you do not want to leave as u minus 5 quantity squared. You need to expand that out. U minus 5 quantity squared is going to be u squared minus 5u for minus 10u, and then you'd have negative 5 times negative 5 for plus 25 in the last term. If you ever need to go ahead and FOIL out the group u minus 5 times u minus 5, please do that. Don't make the mistake I've seen so many students do and say, well, isn't that just u squared minus 25 or something like that? It's never just the first term squared and the second term squared. It's always going to be a trinomial. So I get my correct algebraic trinomial from squaring out the group u minus 5 in the numerator. My denominator is just going to be u cubed. The nice thing about this is it algebraically simplifies. I can distribute that u cubed into each term in the numerator. When I distribute it to the first term, I'll get 1 over u. When I distribute it into the second term, I'll just get minus 10 u to the negative 2. And then into the third term, plus 25 u to the negative 3. The reason I didn't call this first term u to the negative 1 is, remember, that's the exception to the power rule. The integral of 1 over u is the natural log of the absolute value of u. The other two I use the power rule on. So I'll have minus 10 u to the negative 1 divided by negative 1. That's why that's becoming plus 10 u to the negative 1. And then my last term would be plus 25 u to the negative 4th over, not negative 4, you add 1 to the exponent, John, plus 25 u to the negative 2 divided by negative 2. That's why you'll see I have minus 25 over 2 u to the negative 2 plus the constant of integration. Now, this answer, two things wrong with it. One, it's in terms of u, and secondly, it's sloppy to have negative exponents in your final answer. So I got rid of both of those in one step here. I said we know that u is equal to x plus 5, so this is just the natural log of the absolute value of x plus 5. This is going to be plus 10 divided by x plus 5 to the first, and then we have minus 25 over 2 times the group x plus 5 to the second power, plus your constant of integration. Gorgeous format of an answer there. Now, we had tangent as an earlier problem. We already saw that that was required substitution in and of itself. I'm using it in this problem to show a use of double substitution. It would have been possible to do this with one substitution, but I kind of wanted to show it with two here. Typically, whenever we do substitution, we say it's whatever's inside of a function. So the obvious choice for substitution in my number 13 example here is to let it be the angle x to the 4/5 power. If I do that, I can say, well, then the derivative of x to the 4/5 is going to be 4/5 x to the negative 1/5 power, and that's going to be the derivative with respect to x. So I'd have to see a 4/5 x to the negative 1/5 dx in my problem. And I need to understand, if I have an x to the 1/5 in that problem, in the denominator, I have an x to the negative 1/5. So that term is already there, but there's not a factor of 4/5. So what I've done from this step to this step is I've just rewrote the denominator as x to the negative 1/5. I need it to be multiplied by 4/5. So I'm multiplying the inside by 4/5. I make up for that by multiplying by 5/4 on the outside. Now, this 4/5 x to the negative 1/5 dx becomes du in my next step. My tangent of the angle becomes tangent of u. So I have 5/4 the integral of the tangent of u du. Now, I went ahead and wrote that as the sine of u over the cosine of u, just like we did earlier. And I'm going to use a double substitution. Typically, when we use substitution more than one, and you can't use u as your substitution variable again, some people would use t. That's a often choice for substitution. You can choose u, you can choose t, you could use p. That one's used every now and then. What I like to do, just to keep it straight, is first substitution I use u, second substitution I use w. So for my second substitution, w is going to equal the cosine of u. Well, the derivative of w would be the derivative of the cosine, which is negative sine of u du. So now I could go into my problem and say, well, then that denominator is going to become w, w is equal to the cosine of u. And so whenever I'm going into this problem, that denominator is going to become w. My numerator, the sine of u, I shouldn't have w as a variable here. These variables should be u. My w's are over here. This numerator, it needed to be the negative sine of u du. So I multiplied the inside by a negative. I multiplied the outside by a negative. Please do keep in mind, though, that this is not a w in this step. This is still u. All of those are now they're ugly u's. But that numerator, the negative sign of u du, all of that becomes dw. My denominator, the cosine of u, that becomes w. So I have negative 5/4, the integral of 1 over w dw. We know that that's the natural log of the absolute value of w plus c. Have that multiplied by negative 5/4. Well, now I back substitute. I know w is equal to the cosine of u. So now it's the natural log of the absolute value of cosine of u. Back substitute again. I know that the u in that problem is equal to x to the 5/4 power. So inside of that cosine function, the angle needs to be x to the 5/4. So my final answer, the integral is negative 5/4 natural log of the absolute value of cosine of x to the 4/5 plus your constant of integration. Another problem here to look at with you. When I look at number 14, I have the integral of the cosine of t times the cosine of the sine of t, and I'm integrating that with respect to t. Should be no question what your variable of substitution is going to be. We usually let it be what's the innermost part of the function. Well, this sine is inside of the cosine, so I can say that needs to be my u substitution. So I'll let u equal the sine of t here. And then when I do that, I can say, well, the derivative of the sine of t is the cosine of t with respect to t. Do I see a cosine t dt in my problem? Yeah, cosine t dt right there. So I know that this is going to become the integral of the cosine of, instead of the sine, it's of u, and then cosine t dt all becomes du. This substitution made this problem very easy, because now the integral of the cosine of u is just the sine of u plus your constant of integration. Back substitute, we know that u is equal to the sine of t. So please don't make the mistake. I could see somebody accidentally saying this is the sine of t times the sine of t. Absolutely not. U is the angle of this sine function, and u is equal to the sine of t in and of itself. So we have the sine of the angle, the sine of t, plus c for your final answer there. That's a gorgeous problem. Now, for number 15, back to a definite integral. We have the integral from e to e squared of dx over x times the group, the natural log of x quantity squared. Okay, so if I'm looking at this, I can go in and say, I'll evaluate this from e to e squared after I do my integration, turns it into other terms. When I'm looking at this, the innermost part of this function, I see that natural log of x is inside of a group to the second power in the denominator. That tells me that u most likely needs to be set equal to the natural log of x. It's a gorgeous choice here, because you see, if you let u equal natural log of x, derivative of u, derivative of natural log is 1 over x dx. Do you see a 1 over x dx in the problem? Of course you do. 1 over x times dx. Now, you could rewrite this problem as 1 over x times dx times 1 over the natural log of x quantity squared. That's why all of that 1 over x dx I'm replacing with a du. The natural log of x quantity squared in the denominator becomes u squared in the denominator. Now, just like I was saying at the beginning of this problem, I'm trying to integrate from e to e squared. Well, now those were limits in terms of x. I need to get them in limits in terms of u. So I change my limits of integration. U evaluated at e is the natural log of e, which is 1. You evaluated the upper limit, e to the second, is just your 2. So instead of evaluating from e to e squared, we're evaluating from 1 to 2. When we integrate this, this is the same thing as u to the negative 2. So its integral is u to the negative 1 divided by negative 1, which is the same thing as negative 1 over u to the first. Now we're evaluating that from 1 to 2. We get negative 1 over 2 minus negative 1 over 1. Clearly that's going to be plus 1. 1 minus 1/2 is an answer of 1/2 there. Now, last page I want to look at here with you. Let's say for number 16 here, we're looking at the integral of the cotangent times the natural log of the sine integrated with respect to x. Very easy here. You might say, well, hey, how about I let u equal what's inside and be the sine function? The problem with that, and it wouldn't be wrong, but it would then require another substitution after. So if you wanted to do the most efficient substitution in this problem, you might consider letting it be the entire natural log. Notice when I did that, notice why I did that. I said derivative of any natural log is going to be 1 over what's inside the logarithm times the derivative of what's inside the logarithm. So the derivative of the natural log of sine of x is 1 over sine of x times the derivative of sine, which is cosine x. I'll get cosine x over sine of x. Well, cosine over sine, that is cotangent. So in other words, the derivative of u is cotangent x dx. I have a cotangent x dx in my problem. That cotangent x dx all becomes du in this step. Well, then this natural log of sine of x is just u. This simplified so easily to just be the integral of u du. We use the power rule. We get our u to the second over 2 plus the constant of integration. And now when we're evaluating that, though, we could write this as 1/2 times the group of u quantities squared. Well, u is the natural log of the sine of x, group squared plus c. Now, quite often in these problems, students, whenever they see their answer involves a natural log, they'll think, oh, I've got to put absolute values inside of that. No, you don't. The only time you put an absolute value inside of a logarithm is whenever you're integrating something like 1 over u to get the natural log of the absolute value of u. This logarithm was not a result of the integration. It was a result of plugging the substituted value back in. So you don't need any absolute values in this problem. Now, for number 17, we have the definite integral from 0 to the square root of e minus 1 of x cubed over x squared plus 1 with respect to x. Typically in a fraction, you'll always let u equal the denominator. So if I let u equal that denominator, x squared plus 1, its derivative would be 2x with respect to x. So I'll look up at the numerator and see, I don't have a 2x dx up there. I have an x cubed dx. So I tried to show my thinking out in this next step. I needed a factor of 2x dx in order to do this substitution. From this step to this step, that 2x dx is going to become the du. So I also had to concern myself with, well, what's that x squared going to become? That's what I did right here. I said, well, if u is equal to x squared plus 1, then x squared is equal to u minus 1. So that x squared here, I'm replacing with a u minus 1 in the numerator. The 2x dx becomes the du. Of course, my denominator, x squared plus 1, just becomes u. Now, I know how to simplify all of that into terms of u, but I can't leave my limits of integration in terms of x. So I had to do that as well. My lower limit was x equals 0. When you plug that into u, you'll get 0 squared plus 1. Your lower limit is now 1. Your upper limit, that square root of e minus 1, it's going to become the square root of e minus 1 squared, which is just e minus 1, and then you have plus 1. So I get e minus 1 plus 1. That's just going to be e. So I'm integrating from 1 to e of u minus 1 over u, and we're integrating this with respect to u. Now, as soon as I see I have a fraction with 2 terms in the numerator, I can distribute that term in the denominator into each term in the numerator and say, I'm just going to integrate u over u, which is 1, minus 1 over u. The integral of 1 with respect to u, remember 1 is the same thing as 1 u to the 0. So the power rule says that that's going to become 1 u to the first. I get that right there. The integral of 1 over u is the natural log of the absolute value of u, and we certainly need that absolute value inside of that natural log. And all of this is multiplied by 1/2. Now, I was saying we certainly need that absolute value. We would, but in this problem, it's not as big of a deal because both of my limits of integration are positive anyway. So it wouldn't have been horrible if I didn't put it. Now I need to evaluate. If I plug the e in, I would get e minus the natural log of e, which I know is e minus 1. That's the upper limit. Minus when you evaluate the lower limit. Well, that would be 1 minus the natural log of 1. Natural log of 1 is 0, so I just get 1 minus 0 there. So on the inside, upper limit minus lower limit, I'll get e minus 1 minus 1. That's going to be e minus 2. So I'll have 1/2 times e minus 2. You could leave it like that. You could call it e minus 2 over 2, or what I did is I distributed the 1/2 to call it 1/2 e minus 1. Any of those answers would be fine. Now, I assure you on a problem like this, Achieve will want an exact answer. So I would want to leave it like this as opposed to getting a decimal approximation to that. Okay, this should set you on a path to be able to work these substitution problems. Let me know if you have any questions. I really want to make sure you're comfortable with this section. It is by far the most important section that we'll be looking at this semester. Once you get accustomed to working these problems, I think you'll actually enjoy yourself working these substitution problems. And now we have another section with substitution coming in 5.8 that'll look at some more difficult problems that we haven't done in this section, namely our inverse trig integrals and stuff like that. It's really not bad though. So stay tuned for section 5.8 where we do substitution part 2.